Okay, let's get back to where we were at the end of the last lecture, where I was scratching my head trying to figure out what was going wrong. We had this bit process program where we defined BP echo that receives a bit and then echoes it. And then I defined states to be waiting for a bit before saying how to continue. And I defined a sort of step operation that would effectively, that I could feed to the main loop for the Haskell program. And I defined a current state as waiting for a bit, and if we get true, it should continue by echoing twice. And if we get false, that's 0, it should continue by echoing once. And then I've plugged that into my main loop with that as my starting state and my general step operation. And when I ran it, let's just recompile, although I think I am recompiled. I hit 1, and then it should echo twice, but it only echoes once. And I hit 0, and it should echo once, but it echoes twice. So that is clearly not the intended behavior. And I spent quite a lot of Friday afternoon staring quite hard at the code for my program, wondering at which point I jumbled up a true and a false to get that behavior. And I couldn't find the problem anywhere. So then I turned my attention to the way the Booleans were set up. Maybe I'll just search for it. And you can see what I've done here. I've got my declaration of my Boolean type 2 with constructors TT for true and FF for false, and I've communicated that to Agda with these built-ins. And I was wondering if there might be something a bit amiss with the way this built-in directive is implemented. So I thought I would try the alternative, which is directly to say exactly how GHC should compile my 2 type. In particular, that it should map my 2 type to the Haskell data type bool with the constructors TT and FF mapped to true and false respectively. So that's fine. And now I better recompile. Recompile. And now, when I run the program, if I hit 0, it echoes once. And if I hit 1, it echoes twice, which is what we wanted. So what on earth happened? I changed the code. You can see with these built-in pragmas, I was telling it which one is false and which one is true. The trouble was that the code that implements this built-in bool pragma in the Agda compiler ignores which one you say is false and which one you say is true, and assumes that the constructors are given in the same order as they're given in the Haskell library. And in Haskell, they put the false first. So it was assuming that there was a direct in-memory translation between 2 and Haskell's bool, but with the constructors in the wrong order, that's not true. So of course, that very afternoon on Friday, I filed a bug report, and indeed, this guy, Ulf Norell, who is a good friend of mine and who is the author of, he's the main developer of Agda. He recognized that it was a legitimate bug, and he managed to write this program, which, if you ask it, is the string foo equal to the string bar prints true. So that's now a recognized Agda bug. It'll be fixed in the next release, I'm sure. Hi, Ulf. And that's hopefully the end of that matter. It's always funny when you spend a while looking for what went wrong and it wasn't really your fault. That's life when you work with, prototype software. The more serious thing that I kind of messed up slightly, and I realized at the time I wasn't very happy, was this decision to treat the state as something that was always waiting for a bit. And that was partly because I chose the wrong translation, really. I was saying we're always going to interpret something that when it gets a bit gives you some output and carries on. So if we have to start by waiting for a bit, that means we can never start by doing some output. We always have to start by doing some input, and that's a bit of a nuisance. So what I should have done was to interpret a bit process in general as something which first produces some output and then either stops or asks for an input before carrying on. That's a much more sensible interpretation of a bit process. So how do we do the interpretation? Well, if our process says stop, then we produce no output and we don't carry on. If the process says send, then we see what the rest of the process does and we glue the bit we're sending to the start of the output. If the process says receive, then we produce no output and we say yes, we will continue when we get a bit, and once we see the bit, that will tell us which process to continue with. So that's a more sensible way of doing it, and now I can give any bit process I like. So if I uncomment this main, I better comment out the other one. So you can see this process sends us a prompt, which is a 0, and then it echoes twice. So if I compile that, and then run it, you can see we've got our 0 straight away. We didn't have to wait for an input, and now I can hit 1 and 0, and then it stops, so it echoed twice. Okay, so we've managed to make it in a small way, all the way out. We've got our bit processes, which are not very spectacular, but the idea is enough for the time being. In a couple of weeks' time, we'll work with processes where instead of inputting bits, we input keystrokes. And instead of outputting bits, we output characters so that we can interact properly with a shell, with a terminal. And what's more, we'll switch on enough anti-escape codes so that you can do things like position the cursor in anywhere you like in the shell window, and even produce colored text and stuff like that, at which point it will become possible to write applications that run in a terminal. So this is kind of funny for CS410. Usually it's nowhere near week 6, week 7 before we're actually running programs in a terminal and thinking about how to write applications. So this is the most practical edition of CS410 ever. But it's also the most theoretical issue of CS410 ever. It's the most we've been engaged with the theory of monads. But it's monads that make it all happen, that characterize processes which can do stuff in order to compute a value. In this case, inputting and outputting. Okay, so hopefully that's that chapter closed. What I want to do for the rest of this lecture is look at the ideas that I'm asking you to engage with in exercise 2. As you will have noticed, well, the rest of exercise 2 turned up in the repo. I spent Sunday hacking like crazy to make that happen, and I didn't get as far as writing a window manager in exercise 2. I decided, I reached a point where it was full enough already and I stopped. So we'll get to that later. But the important ideas are there. And the key thing that we're going to do is change which category we're working in. We're not going to change anything else about the tools and structures we work with, but we're, instead of working in the category of sets and functions, we're going to work in the category of indexed sets and index respecting functions. And that's a thing we can do because we've got dependent types kicking around. So that what we need to do is get familiar with what's going on there and why nothing terribly important has changed, but something useful has happened. Okay. So what are these things? What are the objects of this category? Oh, well, here we are. The objects of this category are these I arrow set things. So instead of the objects just being sets, they're sets that are indexed by values in some index type I. I is for index here. So what does that boil down to? Well, the idea is that the index characterizes some important information that stuff has to be compatible with. So what we're saying is an I arrow set tells you for a given I which things would be compatible with it. So like we're used to, for example, vectors. When we fix the element type, we get something in that arrow set. And a vector is only compatible with the number if it's the right length. So we'll be using the ability to index to ensure compatibility with important application information. For example, the dimensions of the screen. If you know that width and height of the screen, then you know what size of a display your application ought to be manufacturing. You know, we want our displays to be some sort of rectangle thing, but it has to fit the size of our terminal display. It's got to be compatible with those sizes, and now we can do that. Okay, so what are the morphisms that go to the object? The morphisms are these things. So let's unpack that. In fact, what shall I do here? Let's see if I can get it to display. See if that works. Yeah. So what I've just I fixed the index set to be nat, and I asked for what is this arrow thing in this category. So S and T are sets indexed by natural numbers, And the morphisms are things which say whatever index we're working at, whatever number we're working with, maybe whatever the size is, if you give me an S which fits with that, I'll give you back a T which fits with that. So instead of just saying, you give me an input, I'll give you an output, it's you give me an input which is compatible with the index, and I'll give you an output which is compatible with the index. And we have to know how to do that, whatever the index is. Yeah?
So what's the difference between S and T? There's no difference, it's just the I is the same?
The I stays the same, but the S, so for example, let's see, S might be matrices which are square matrices of side I, and T might just be vectors of length I. And then this would be saying, if you give me a square, so for example, the diagonal of a square matrix would take a square of size of side I and give you a vector that's just exactly I long. But what we're enforcing is that compatibility.
So if we had the graph with the dots, basically we would have dots of different kinds, and then they all have the same I. Is that one?
Yeah. So so if we're drawing pictures, right? The points in the graph, the objects, are things which depend on I. So we're saying you can almost think of it like conditions, right? Is this a property of a given index? That's another way of looking at it. If you pull this through the Curry-Howard correspondence, you can think of the index as the state of the system, and then our S and our T are like a precondition and a postcondition. What we're saying is, if the precondition holds, then we can deliver the postcondition. So we're actually really working with a type system that has imported an aspect of program logic. We can really talk about the state of the system or the size of the display and really enforce that what happens is somehow appropriate with respect to some relevant notion of what's going on. So let's just check. Do we have identity and composition for these things? Well, at every index we have the identity function. And at every index, so f and g map an index to a function, but we know that function respects index. So if we've got f and g, then at every index I, we can compose f of I with g of I. Yeah?
Why does I need to be not there?
I just needed to give it something in order to make it print something out. I just had to, in order to project that field, to project this field from a category built like this, I had to feed it a type. Okay, so we're now working in the world of indexed things. And one of the things that I ask you to do in exercise 2 is to build this crucial functor between two different categories of indexed sets. So here, we're going to, our output is going to be sets indexed by lists of stuff, and our input is sets indexed by list elements. So what do we get? We get some argument P that represents, if you like, a property of an element. And then we give back the type that represents knowing the property for all of the elements of the list. So we'll see an example in a moment, but let's just figure it out. When do we know P for all elements of the empty list? Well, we already do, because there's nothing to know. That's easy. When do we know P for all elements of X cons X's? Well, we better know P of X, and we better know that P holds for all of the X's. Okay? So let's just have a wee example. I've got no idea how many examples I've got, so I'm just picking numbers at random.
Just quickly, what's the asterisk again?
That's building the type of ordinary pairs.
Right.
Oh, how come it doesn't know char? I thought it did. Did I do that? Okay, well if it doesn't know char, I'll just use bits. We know it knows bits. Okay. So what I'm saying here is that for every number in this list, I need a vector of bits, which is that long. So let's see that in action. You can see that, I mean, this is just a program, it's just a recursive program. So when I look at the goal, it actually runs the program and computes the type of what we want. We need a vector of 1 bit, paired with a vector of 2 bits, paired with a vector of 3 bits, paired at the end with an element of the 1 type. So I can start by saying that something, comma, something, comma, something, comma, void. And you can see each of my sub-goals are asking for a vector. So maybe I can give this true cons null, new line, true cons false, cons null, true cons false, cons true, cons null. So you can see that we've built a funny kind of list where not everything is the same. Not everything's the same type, but everything's compatible with the individual elements in the list index. So we're saying the index that tells us what would be appropriate are this list 1, 2, 3. And then the things that have to fit are these vectors of what being appropriate means, being a vector of the given length. So that will turn out to be useful very shortly. And you can see, I hope, that what's this data structure really doing? It's really packing up elements of types given by P, appropriate to whatever index shows up in the list. So if for every index we know how to map a P for that index to something else for the same index, if we know for all I, P of I implies Q of I, we should be able to turn one of these things full of P's into something full of Q's. We know that whatever index this thing fits with, we can map it to something that still fits. So we're going to spend time thinking about that. Okay. But then we get to something that's really cunning and useful, and which I learned pretty much from Peter Hancock. I don't know if you've encountered Peter Hancock. He occasionally visits us. He was one of the first people ever to implement a type system with dependent types back in the 70s. He also worked for Digital back when they were developing the first VMS operating system. So he's one of the people who made virtual memory really happen in operating systems. And he spent a lot of time thinking about how to do interaction in type theory. This is a simplified version of one of his ideas. What's going to happen is that we're going to describe a general way to think about building functors between indexed sets. So in a moment, we're going to build something. We're going to turn a C in this type I arrow O, or I triangle O. That's going to give us something that takes an I to set to an O to set. So now I want you to think of O as meaning the outer index, and I as meaning the inner index in some situation. So the idea is this. So you can think of the outer index as telling us the shape of some whole structure that we want to build. And we're going to build it from pieces that have inner shapes. So what we need to know is, given an outer shape, how we can cut it up into places that have inner shapes. So here's what happens. You first of all, for any given outer shape, give the set of ways in which you can cut it up. And we'll see examples of that in just a tick. Then, once you know which way you have chosen to cut it up, you have to know how to give back the list of the inner shapes of the pieces that you've cut it into. So here's one example. We're going to use this to build a copy of the vectors. So the idea is that the outer shapes, which are the shapes of vectors, are natural numbers. And the inner shapes are just going to be given by the unit type, because we don't have any particular requirements for the shapes of the elements that we put into vectors. Okay? But we can explain how we can cut up a number into the appropriate collection of pieces. Right. We know that the number of elements we want exactly determines the number of pieces we want, the number of things we want in the vector, yeah? So that means there's exactly one way to cut up every number. And then when we see the number and the boring way in which we chose to cut it up, we can give a list of the shapes of all of the pieces just by giving n elements of the unit type. So we basically write, what we're really doing is describing, by giving a list of elements of the unit type, we're writing a list that has placeholders that shows where the elements are going to go. Here's another one, another example which we will make heavy use of. This time, the outer shapes are natural numbers, and so are the inner shapes. And what we're saying here, now that cuts choice is much more interesting, we can say that you can cut up a number mn by giving two numbers, m and n respectively, as long as they add up to mn. So we're saying you've got this much, and you can cut it anywhere along its length. And then what pieces do you get? Well, you look at the m and the n that you chose, and you say, there are going to be two pieces. We've cut our length in two. The first piece is going to have length m, and the second piece is going to have length n. So we're saying we can cut a length into two pieces that add up to the original length. Okay? Is that making sense? So we're going to use that in due time to, well, we're going to figure out how to generalize this to 2 dimensions, actually to anything, and then we're going to start using it to cut up the screen. We're going to be talking about things which fit into the screen size, which we can cut up in either dimension. We can either cut it up into 2 horizontal pieces that have the right height and fit together to make the right width, or into 2 vertical pieces which have the right width already and which add up to the right height. So that's one component. Okay. So how do you build the structure that we care about? Let's see. So this structure cutting is parameterized by one of these how to cut stuff up things with outer shape and inner shape. And it says, if you know what the inner pieces are the P's, and you know what the outer shape is, how do you make something from pieces that fits the outer shape? And you have to provide 2 things. So I've got an infix constructor, which is ASCII art scissors. And the first thing you have to do is choose which of the ways that you are allowed to cut up the outer shape. You choose a way. And then you've got this function inners that computes the list of the shapes of the pieces. So you use that for your chosen cut. And then you have to give all of the pieces. For each inner shape, you have to give an inner piece. We're trying to achieve inner piece. And so let's immediately have an example of that. Maybe I will give, let's see, example for, is going to be a cutting, nat cut, and the pieces will be, let's have them bit vectors again, and let's say we're going to start with outer shape 5. Okay, so how do I build a cutting? Well, I first of all use my scissors constructor, and on the left I have to give 2 numbers that add up to 5. Let's have 3 and 2, and you can see here I have to give a proof that 3 plus 2 really equals 5. Fortunately, REFL 5 will do nicely. So now what do I have to give here? I've got to give a bit vector that's 3 long and a bit vector that's 2 long. So I can say, so maybe I'll give trues for the first one, and falses for the second one. nowhere in any of the technology that you usually program user interfaces in does like the size of stuff actually determine what you're allowed to do. You're just supposed to get that right magically. Nobody checks that the stuff that you're going to splat onto the screen actually fits where it's going. And correspondingly, it's very, very easy to screw it up. And people screw it up all the time. I mean, even in seriously released software, you get these kind of visual glitches where sizes are just managed badly. We shall have an end to that. Okay, so where are we going with all of this? We're using cuttings repeatedly to build what I call interiors. So now, what happens? Crucially, we're parameterized by a cutting, by one of these triangle things. I guess I'll call them containers, where the inner shapes and outer shapes are the same. And what that means is, since the inner shapes and outer shapes are the same, we can keep on cutting for as long as we like. And then we say what tiles we have available to tile the interior of a shape. So that's this T is for tile, and they are indexed by something. You can think of that as the perimeter. Okay, and we know the perimeter of the whole thing that we're trying to tile. So we've got two constructors. One says, if you happen to have a tile that exactly fits the perimeter, you're in luck. That single tile will give you the entire interior. But even if you don't, or even if you do, you have an alternative possibility. You can take the perimeter you're trying to fill, and you can cut it up by any way the cutting lets you do. So anyway our C container lets us cut stuff up. And then the pieces that you put on the inside have to be more interiors. So if, for example, we had our two-dimensional version of NapCut that allowed us to make horizontal cuts or vertical cuts in a rectangle, we could basically describe a screen layout by repeatedly making either horizontal or vertical cuts in the shape of the overall rectangle until we get down to the individual framed pieces that we care about. And those would be our tiles. Now, you notice that we've got some parameter t from I to set, and then this tile constructor just says, if you have a t, you can pack it up as an interior. And then we've got something which says, oh, and you can make bigger interiors from smaller interiors. Does that ring any bells? Like bit processors where you've got some notion of parameter, and then there's a constructor that says if you've got an element of the parameter, you've got a process. And then some other constructors which say, you can make bigger processes from smaller processes. Yeah, it's the same deal. It's the same deal. No matter what C you choose, interior C will always be a monad. If you think about what we need to make a monad, so if we think of these interiors as tilings of the interior of some perimeter, we need to be able to say, well, if you have a tile, a single tile that fits the perimeter, that gives you a whole tiling. That's what the tile constructor does. And you're going to need some sort of multiply, something which, or join, which says, if you can tile an interior with tilings, so if you've got sort of 2 layers of tiling, so your outer layer has, as its tiles, more tilings that still fit in the rectangle, then you'll be able to merge both layers down to a single tiling. So it's kind of quite visual. We're filming this one, right?
Mm-hmm.
Okay, so let me just grab a pen and kill one projector.
Does that tile constructor, does that work for ones that are smaller than the given size as well?
No.
Does it have to be bang on?
No, it has to be bang on. But we'll be able to figure that out by giving you, so for real applications, you actually need blank tiles. So then, if your tile's not big enough, you can pad it out with blanks to fit. And in fact, we'll also be able to do all sorts of stuff with tiles that are not merely blank but transparent. Yeah. So the situation is that you might have an outer tiling which might look like that, perhaps, and then each tile in the outer tiling is an inner tiling.
Can you make the lines double width?
Yeah, probably. Yeah, so you've got some situation like this. Where each tile in the outer tiling is itself an inner tiling made from red tiles. And then you've got a join operation that is simply going to consist of turning the red lines blue, but keeping everything in the same place, so that you've got only one layer of the structure. And it will look an awful lot like what you're familiar with. Let's finish by just doing a couple of little examples. So what I want to do is to build a copy of maybe such that so this is going to be a copy of maybe built as an interior. I've decided, so the indices are going to be boring, right? So if your index set has exactly one element, it's the same as really not having an index set at all. There's no difference between any of the indices. So it's just a copy of working with sets. So we haven't thrown anything away. So we need to figure out, I guess I better let's see if we can rebuild the constructors. I bet, haha. That is the type of no. Better manage my colons correctly. Okay. So we need, what I'm trying to say is, can we just come up with one of these things so that this type behaves just like maybe? So let's first of all see if we can implement yes. Well, so remember, yes is how we give a final value. So that should be the same job as, if we've actually got an x, then we should be able to build our funny interior, even though we don't know what the cut is. That should just be tile x plays the role of yes. Okay, so we've got an element which you could think of as having the only possible index, and we need to produce an interior with the only possible index. So our tiles are elements, and we can turn a tile into an interior with the tile constructor. So now we have to figure out what our structure is that allows us to make sure that there's exactly one way to make a no. Okay, so I just gave the game away. Right, we can't say this is the empty type because we have to give something here. But we only want one no. So let's say that there's one way to cut up the perimeter. But then afterwards we have to say, what are the pieces when you cut up in that way? Well, what are the components packed up inside a no? Well, there aren't any, so that's fine. We just give the empty list. So now we can say it's going to be made by cutting, and I have to give a scissors, and then here I've got no choice. I've got to give the only possible cut, and here I've also got no choice. To give all the pieces, I just give the element of the unit type. So it's a slightly funny looking no, but it's a perfectly good no. Okay, so guess what, folks? Not only is the interior monad that I'm asking you to build, generally useful for applications and stuff, it already eats one of the monads we already built, right? If we know interiors are always monads, then we know this version of maybe is a monad without even having to ask. Maybe we can do the same sort of thing with bit processes. Again, there's no interesting state, so the indices are going to be 1. I've got to watch the time here. So we know that the tile constructor is going to correspond to stop. So we just have to explain the ways in which you build bigger bit processes from smaller bit processes. Yeah? So how was that again? You could either send a bit, and you had to choose which bit to send, or you could decide to receive a bit, in which case you didn't have to specify any information, you just had to wait for the bit. Okay, that's fine. That means there are 2 possibilities, so it's something or something. What's it? Oh, I've got to ignore my state. Okay, there's 2 possibilities. For the send possibility, you have to tell me which bit to send. For the receive possibility, you don't have to tell me any more information. And now we have to say what the pieces are. So I'm going to have to do that because we've got our choice of cut needs pattern matching. Okay, So we use the left option to code for sending. So if we've got in left, then the chosen cut was a send operation. How many pieces have we got? Well, when we chose to send, we always just said what one process we were going to do after the send. So we better give back, we're asking for one sub-process in state void. However, if we chose the receive command, then we're going to need two processes for what we do if we get true and what we do if we get false. So we can ask for that by saying there are two pieces, each of which stays in the same trivial state. Okay, I've got to stop there, but my point is that, yes, the other monad that we were working with is also an instance of the interiors. So, goodness me, you're going to build an extremely powerful general tool that doesn't just give you one or two monads we care about, but absolutely loads of monads that do all sorts of important things.